today I'm going to be talking about human and autonomous robot teaming on Mars, and particularly in the context of the Mars 2020 mission. And I know there are a number of talks on the science aspect and the Mars helicopter, so I'm going to be focusing on the Perseverance rover. In general, more focus of this is just talking about how we've really been able to make enormous strides in the autonomous capabilities because of this human robot teaming. And I like to say, on Earth, we are making strides in human robot teaming, but humans had existed on Mars, on Earth actually, for 6 billion years before the first documented robot. And so the system is sort of designed such that robots have had to adapt to it, and it's an inefficient process. Whereas on Mars, it's a planet at the moment inhabited entirely by robots. And it offers, I believe, a tremendous opportunity for us to architect it from the ground up so that we can do this teaming, develop it in a way that is really very, allows us to really go beyond what has been possible in the past. Most of you already know this, but I am going to see if I can move my slide forward. Yeah. So most of you already know the concept of the Mars sample return mission, of which the Perseverance rover is the first step. So Perseverance is collecting and caching sample cores, and we're going to have a subsequent lander land on Mars. And the lander, this is a joint partnership between NASA and the European Space Agency, ESA, has the 7 degree of freedom robotic arm, which is going to reach out and get the sample cores from Perseverance. And then we're going to put them in a canister, launch them, a rocket from Mars for the first time. It's going to rendezvous with an Earth return orbiter and then bring them back to Earth. Because of the great success with Ingenuity, we now have 2 helicopters as a backup option on the Mars sample return mission. And you're seeing here in the illustration, sort of an Ingenuity scale helicopter, but it's got wheels and an arm, and there's 2 of them. And those will be used to collect as a backup the sample cores and bring them to the workspace of the lander so that they can be transmitted. And I'll talk about that a little bit more. So going on to, let's see, going on to the next slide, when we wanted to bring samples back from Mars, scientists got together and said, if you're going to bring the first ever samples, we want to bring them from the most interesting place. And the most interesting place ended up being Jezero. But Jezero has this crater, which has an ancient river delta, which has a very high probability of preserving signs of ancient life. But the crater also has walls that are tens of meters. And so we used for landing in that zone, so we wouldn't land in a hazarded area, autonomous capability called terrain relative navigation. And I was showing this video where as we were landing, we could detect if there were hazards and divert from it. And on the landing day, we actually did encounter a hazard in Jezero and ended up landing, doing a divert. So this is showing the crater, which we diverted from. And as a result, the landing site is on the other side of this hazardous zone. And this was a great opportunity. And so we, after doing the checkouts, doing Ingenuity sort of demonstration of the technology of the helicopter, we started a science campaign and used the opportunity to do a crater flow campaign in the South Theta area, which was really, had a lot of science value. And this image here is showing where the landing site was, and in the white, you're seeing the rover's traverse path, and the white are the locations at which the rover stopped, and the red crosses are the areas in which we have collected samples. Once we were done in South Theta, the really interesting region, which is why we'd gone to Mars, was the Delta. And so, essentially what science would love and what we want to do for Mars exploration is essentially say, can we just teleport the rover to the Delta now that we're done? Except we were over 5 kilometers away from it with, a pretty large 1-ton rover. And we ended up doing this rapid traverse, which you're seeing all the way across around to get to the Delta. This was over 5 kilometers and would typically in past mission have taken, in the order of a year, a little less than a year to get there. Whereas Perseverance was able to do that in 31 days. And that really sort of broke all kinds of interplanetary records for us to be able to do that. And I'm going to go into a little bit of how that was possible. So why is it challenging to get a lot done on Mars at the moment? It's because of this time delay, which most of you are well familiar with, is that we have to go through the Deep Space Network to talk directly to the rover, and then we collect so much data that it has to come through the Deep Space Network back. On top of that, there's a very limited time in the day to actually drive. So I'm just showing an example from one of our plans. This is just a fraction of it. So on the left, you're seeing all the activities, and along the x-axis, you're seeing a cascading effect of the sorts of things we do. And this is a real plan where in the beginning, you'll wake up, and you don't want to wake up too early on Mars because it's very cold and you're going to spend a lot of energy just heating things up. So we wake up on Mars and we would do some remote sensing, and then you would do a drive, but you want to get the drive done before you the pass, where the orbiter will pass over, so you can send data back to Earth. So the amount of time we typically have in a day to drive is just a few hours. So in that few hours, humans from Earth, seeing the image of the terrain ahead of them, can actually direct the rover quite well, which is what we've done on previous Mars missions. And if you're driving autonomously, traditionally autonomy was slow, and so we didn't use it much because actually the time to drive is so little that if humans can drive more efficiently, because it was faster for humans to drive, the thinking took so long that we didn't use it as much. So the main goal we were trying to solve is it had to be better. That the capability when you have a human robot team is that the robot needs to be better than what humans can do by low-level controlling, sort of like controlling an RC car. So some of the capabilities in Perseverance that have really allowed this leap is, it doesn't treat the rover as anything under its entire footprint as a hazard. It can straddle rocks. It also has an improved search. So it's not just looking at simple arcs, it's looking like at a more complex network of paths. It's also able to predict what slip will occur, not just estimate the slip, but it utilizes that in its navigation. We also made the wheels better. So autonomy is always going to drive in a little less informed way than humans can, because we have all of this meta information right now. And so the wheels were beefier so that we don't have to worry about that. And we had the capability called thinking while driving, so that we're actually doing the processing of whether the path ahead is safe or we're still turning the wheels. For that, we had to take the images very quickly. So increase the field of view so we don't have to slew mechanically the mass to take multiple images, also fast exposure time. And then the really big part was it has have very fast computing. So we do the stereo processing in FPGA and have a second dedicated computer. So the results of this, which you're seeing here, is this on the y-axis, you're seeing the drive distance, and this is cumulative odometry. On the y, you're seeing the sol. So this shows up to about sol 562. But the proportion of driving in the orange, which is autonomous, is significantly greater than some of the other variants where you use partial visual odometry and autonomy, and the bottom blue, which is just directed. This is completely the opposite of prior missions where we would do mostly directed driving. So in that rapid traverse, which is shown in the middle here, highlighted, we did 90% of the driving autonomously, and overall in the mission about 80, which is very significant an improvement. So humans are trusting the autonomy so much more that we're using it more. And this particular area in South Seda, highlighted in yellow, I'm going to show this was where we did a drive over a weekend. And so it shows how we use human directable elements. So even though the robot can do autonomous driving, often what limits these capabilities are because how do we communicate our intent? Humans still have information that's valuable. So on the left, you're seeing how this is the actual drive, actual tools we use for driving the rover on Mars, which is, we have a suggested path, which you're seeing in the magenta as the autonomous, and the cyan is kind of the directed part. And then we have zones, the geometric boxes you're seeing is where to keep in and out of. And we give that as a suggestion to the onboard autonomy. if when it's taking images on Mars, when at that point it knows better than we do on Earth, it can choose to deviate from the path. And on the right, you're seeing the actual path, and it did deviate. And over 3 sols, so we had one uplink to Mars. This was Sol 350 to 352. We had a weekend, so we could send the plan on at the beginning and then go home. And over the 3 days, because the duration available each day to drive, the rover drove over 500 kilometers. So this is really allows us to start driving in this way while still being able to communicate where we would like it to go. And this is an image from the second sol, end of the second sol of that drive. It shows you the kind of terrain we were driving in with that autonomous driving. And it does an autonomous turn at the end, because when you're driving autonomously with AutoNav, you may be pointed in different directions, but you need to communicate with the Earth, and it may be low in the horizon. So AutoNav will at the end hunt for a position to communicate, which is what you're seeing in the bottom right. That's from this actual drive, when it was hunting for that comp. Now, this other video is actual images taken by the cameras, which are used to do the autonomous navigation processing. So it's doing stereo really fast. These are the images that you use to drive on Sol 200, on Sol 360 for 210 meters. So this is the sort of terrain that it's navigating through, determining where the hazards are. And you'll see at a point where there's a set of boulders on the right, and it will divert away from them right here and not drive into that more hazardous terrain. And another thing that we're doing on Mars is using Aegis for autonomously doing science. As we're driving these long distances, what if there was really interesting science targets and we're going to miss them? Because part of what you want to do, even as you're driving, is you're characterizing what we're seeing. So here, this capability allows us to take a wide angle image, which you're seeing, which is the nav cam taken on Sol 442. And then autonomously on the board, it will figure out what is the most interesting targets for it to shoot with a laser, where you're seeing the red crosshairs are shooting the laser and then taking telescopic images to return to Earth to say, you know, this was interesting, all without Earth in the loop. And this is another terrain where if you just shot the laser in the blind, you might get not such interesting terrain. But because it was able to take a wide angle image, process it to figure out what's most interesting, shoot the laser, and then take the RMI images, we are able to get really good science, even at the end of a drive without Earth in the loop. So now, you know, we have humans trusting the robots to drive long distances and shoot lasers. So this is really a capabilities at the point where we have reached a level of trust where we know that it's going to return a meaningful science as we're doing this autonomously. And then the last thing I wanted to go into a little bit is that it's very important when you do the autonomous capability for it to be adaptable. I mean, we are going to Mars, and as most of you know, it will surprise us. You know, we're going to a place where no human has been. We have a lot of knowledge about it, but we're still learning. And this shows an example of the very first drill hole we did, where we drilled and there was no core. And we realized that the characteristics of the terrain was such that the entire sample had pulverized. And this is another example where we had an anomaly with the bit carousel. So there is a bit carousel on the front of Perseverance, which is how we collect the cores, transfer it, the robotic arm docks with the bit carousel, and we transfer the sample. And then you're seeing on the bottom, there's a second robotic arm inside Perseverance, which extracts that core and then restores it. Caches it after taking some images and doing some measurements. In the middle, you're seeing a picture where we saw that there were some pebbles. And what had happened was when we were doing that transfer, that core had sort of disintegrated a bit and had deposited pebbles. We were able to work around all of these, but it does result in having to adapt, because we will encounter situations that are unexpected, and you're seeing sort of these rock fragments here. So the approach for what works when we do these human robot teamings is also we send thousands of, so you're seeing this is an example, actual plot up to Sol 200 of showing commands we have sent per Sol for different activities, the robotic arm, helicopter, sample caching, and mobility by each Sol. So we can send, over 1,000 commands to do certain activities, but people don't actually think about all of these commands on a daily basis because that would be very error prone. Here is the tools we use. On the left, you're seeing a much smaller set of directed arguments, which we maybe, deviate the path in this way, or adapt when we're doing coring, we might decide to change the levels which we allow. But in general, it's a much higher level commanding, and at the lower level, we can reconfigure it, but we don't deal with it on a daily basis. So we've designed the system to be very adaptable, and that has helped a lot as well. And so here you're seeing the sorts of measurements we have to do with the robotic arm, where we've got an abrasion patch, because the surface of the targets we look at are highly exposed to the atmosphere, and the most interesting science is underneath. And we need to position instruments like Pixel about 2.55 centimeters above the surface with a 45 kilogram turret at the end of a 2-meter arm. So there's a lot of robotic uncertainty we deal with, and position it in contact with rocks for drilling. And there's a lot of unexpected situations that can happen. This was a recent Sol a few weeks ago, where, as you can see, the terrain around changed when we abraded, and it further modified when we drilled an adjacent rock. At the same time, we've been able to, because of the adaptable approach we've used, we've collected 14 cores at this point, and it's gotten to the point where we have a really diverse set of samples and a really exciting cache to return to Earth. And we're at Enchanted Lake and getting ready to consider even deploying those samples at a depot so that we have a backup cache that is available if, say, something were to happen to Perseverance. And then in the inset, you're seeing in the bottom right, Perseverance is going to climb over the delta and continue exploring beyond and continue collecting sample cores. In fact, we've collected duplicate sample cores so that the ones that will be dropping off, Perseverance carries another copy, very similar samples from a contiguous location with the rover. This will, shifting to sample return. So these samples that we're dropping off when the lander lands, these are meant for the helicopter to pick up from this location. So the SRL landing site, the helicopters will fly, pick up the tubes and bring them back to the lander. So essentially it's going to fly into a helipad zone close to the tube and then drive, because the helicopter will have wheels, and then pick up these tubes and then fly back to the lander and deposit them. So this is really an exciting phase. And then Perseverance is continuing to carry the samples, and the prime option is that the lander will land at a location where Perseverance will drive close to it, and then the robotic arm on the lander will extract the samples out of Perseverance and put them in the orbital assembly. So I'll end with that, and then take any questions you might have about the mission so far or related to human-robot teaming. When will the core samples be tested? Where will the core samples be tested when they're returned? Yeah, so the core samples, when they are returned, it's going to be so exciting even just when the samples are returned. When the samples are returned to Earth, they will be collected and taken to a facility where they're going to be kept in a very clean facility. This is the first time we've brought back essentially alien samples to Earth. So there's a lot of protocol behind how they're handled. But after the initial handling, which might actually be done robotically as well, there are going to be laboratories all over the world that are going to be studying these samples for a very long time. Essentially, even now, samples we brought back from the moon are being studied. So these are samples that are just going to be studied all over for a long time. And then,
so
go ahead.
Oh, so in a best case scenario, will you retrieve both the primary samples on the rover and the backup ones that are dropped?
At the moment, the plan is to do one or the other, because there is a limitation of how many samples can go into the canister. So the canister itself, at the moment can carry like 33 samples, and there are more. So the scientists can select which samples they want to carry. But the goal is to land, if Perseverance is still functional at the time, to land really close to Perseverance and collect the samples Perseverance is carrying. And then if it is not functional, then utilize. That's the current plan.
Hello. So in case we have humans on Mars before we do the return mission, will you change the return mission? Because humans can get the course you selected much faster, easier, more of them. So will the mission change if we have humans on Mars?
I think that would be very exciting to have humans. And I think if humans were to get to Mars, I think there's a lot of things for us to think about. And so, that's not currently in the plan, but if they were to get in there, I think that, we would have, between Perseverance, the lander, 2 helicopters, Ingenuity, and the humans. That's like 5 robots and humans up. I think that'd be great. But I think we would think about it differently.
Dr. Verma, one more question, okay?
Hi, thank you for a great presentation. I just wanted to know, if the helicopters had to go pick up the samples, how would they do that?
So the helicopters are going to fly to a location, a helipad within proximity of the cores, and then the sample retrieval helicopters have wheels, and they will drive into closer proximity and have a robotic arm to pick up the core and cache it, stow it, and then fly back to the lander. That is one core at a time.
Okay, perfect. I think we're ready for our lunch break. Thank you so much, Doctor.
Thank you.